Hello, welcome to the OneClass channel. My name is Fejiro, and I am an Honors Bachelor of Science student currently working towards medical school. Today we'll be going over some commonly asked chemistry questions at both the high school and college levels, okay? If you need some homework help or tutoring, you can definitely check out the links in the description below, so that way we can further assist you and really help you get those topics memorized and comfortable with. Alright, so with all that being said and our formalities out the way, let's kick off this session with our first question. Alright, so what we have here, it's asking us, what is a hypertonic solution? Okay, so what does it mean to be hypertonic? Okay, and we'll actually do that comparing three states. We're going to just say hypertonic, tonic, and isotonic and hypotonic. Okay, so with that we need three, I guess, glasses of water. Okay, well, some solution. Okay, so we're going to label this one hypertonic. We're going to make this one isotonic, and we're going to make this hypotonic. Okay, now the thing you have to remember though is that these hyper, iso, and hypo are going to be in relation to something. Okay, and that's the key part. It's going to be in relation to something else. Okay, so with that being said, we're going to add our something else in this. Let's think of just add a little ball there for each one. If you remember, think of that the egg experiment you did, where it's like, you know, when you put an egg in a certain type of solution, either the egg will shrivel up or it will expand, or even like the balloon one, for example. I'm pretty sure that's another one too. But the most common one is the egg, because the egg serves as a very good membrane where it allows relatively easy diffusion of water in and out, but nothing else. So with that being said, okay, we're going to start with the isotonic. Okay, iso, the prefix iso means same. Okay, so if you add solutes, which is going to be marked by these red dots, okay, it's going to be pretty much evenly spread out, as in there's no much difference between what's in the ball and what's outside. Okay, this is what you would consider like isotonic. I could take out the ball, okay, and the solution, in fact, that's what I'm going to do. I'm going to draw out the solution with the rest of them. I'm just going to add a circle. Okay, so this is what it looks like to be hypertonic. Everything is the same. Okay, inside the ball has around the same ratio as outside the ball, which is what they're referring to as the solution. So the solution in this case is isotonic to the ball inside. Now, hypotonic, okay, this means less. All right, so we're going to have here is going to be a difference. So we're going to have quite concentration inside the ball, okay, and it's going to kind of look like this. This right here would be a good example of hypotonic, okay, because the solution is less than what's inside the ball. And remember, this is all in relation to something else. Okay, hypertonic, you probably guessed, would be more. This is where the ball is going to look quite, in fact, I'm just going to draw like two of them in here, quite empty, and the solution is just jam-packed. Okay, this would be an example of a hypertonic solution. The solution has more solutes, so dissolved things, inside relative to the system inside of it, okay, which is going to be like that ball. So here we have the three distributions here, okay. Now if we assume that this membrane, okay, it's like the ball is a membrane that is only permeable, as in only, permeable means it can flow in and out, but it's only permeable to water, and that's a key part, to water. That means the solids can't go in and out. The only thing that can move in and out would be the water. Let's start with the isotonic solution, okay? If the membrane is only permeable to water, it has no reason to move, because everything is already the same. In the hypotonic solution, where it's actually less than what's the system inside of it, water will flow from the surrounding, so from the solution, into the sphere, because that way, when you have now a bigger sphere, it would end up looking a little bit more isotonic, because now you've given it a bigger radius with around the same amount of solids as it started with. So that would make exactly, so that's why water would flow in, okay, because it needs to make up for the concentration of solids. So if you even like did like ratios, for example, it's like A over water, that's concentration inside, and then the concentration outside would be like B over water, okay. So what we want to do here for the hypotonic solution is that we're going to increase the water here and decrease the water here, so that these two will end up equal to each other, because A and B do not change. The amount of solids inside and outside, those can't change, they can't cross the border. So that's what's going to happen there. You will take the water from the outside going in, therefore increasing the water inside of the system, and decreasing the water in the surroundings, okay. And what this does, when you increase the water in the system, you end up with a less concentrated solution, because like you're increasing the denominator. I mean, a less concentrated I guess system in there, because you've increased the denominator. And when you decrease the denominator here for the hypotonic solution, in regards to that, you've now made a more concentrated solution, hence how you're kind of balancing these two out. Now for this, sorry, I'm just going to copy here. The reason why is because for this, in the hypertonic, it's going to be exactly that, but the inverse. So instead of it being where you're going to now, actually I'm going to label it here. So A is concentration inside system, and B is a concentration inside, concentration of solution. Okay, so now the system is in dire need of decreasing the water to kind of match. Okay, so exactly, it's flipped over now, and the water needs to be increased on the outside in order for these to match better, because here the B is already quite high, as you can tell. The concentration of solution is quite high relative to that. So in this case here, you actually see water flow out in a hypertonic solution. So I know the question was only asking about the hypertonic solution, but in order to really understand, I guess, all different types of tonicity, you need to go through all of them, because all of these are in relation to something else. What I did here is that it was system versus surrounding, solution being the surrounding and system being the inside of it. And so that is what we get here. So let's see how we did. Hypertonic solution is a solution that contains higher concentration, so that is correct, of solids compared to another solution. So that's why I compared it, where I put something in there. Sometimes you can also have examples where you draw it out like this, where you do have a membrane right in the middle that's also only water soluble. That's only water permeable, and then you have one side that has like this much and this side that has like that much. Okay, so we have the more concentrated, so this would be the hypertonic, and this would be the hypotonic. You can also have it a split like that if it makes it easier. for you to see. So exactly, and the water will be flowing in and out through here. That's how it would work. But in this case, you would most likely see the water only go this way because it needs to balance out this hypertonic solution. Okay, so with all that being said, let's see what else it says. If a cell is placed in a hypertonic solution, so that's what our ball is there, it's like the cell, there'll be net flow of water out of the cell, and the cell will lose volume. Exactly. And a solution will be hypertonic to a cell if its solute concentration, which is here, is higher than the inside of the cell, and the solids cannot cross the membrane. Exactly. If a cell is placed in a hypertonic solution, water will leave the cell and the cell will shrink, which is all explained in these different diagrams. So if you want to take a quick look at that, as I say, this is correct. You can pause the video even, just really take some nice notes. But other than that, let's move on to question 2. Oops, don't know how that happened. Question 2. What is hyphen notation? Good point. So, hyphen notation, there we go. Okay, is another notation form for isotopes. Okay, that's key because the other notation form, I believe I discussed in one of my other videos, was a subscript, superscript, subscript, where it's like, for example, if we had carbon 13, okay, this would be its superscript subscript notation. Okay, in order to get this over to a hyphen notation, actually all you do is focus on the superscript, and that is indicated by its mass, the atomic mass of that carbon of that isotope. Okay, that's what that number up there is. So for hyphen notation, you would really just have carbon dash, which is a hyphen, 13. This is effectively the hyphen notation for any compound you come across. So let's say if I made up a compound, actually, in fact, we're going to work with that. We're going to use A and B and then X. So we have an element X, okay? It has A amount of protons, also known as, it's the A element on the periodic table, and it has B for its total atomic mass, okay? The hyphen notation for this would just be X, I guess, full name, hyphen B. In fact, what is a variable? There we go. We're going to call it variable X. Think of that as the full name for X. Variable X dash B. This will be the structure here for its hyphen notation, okay? And we can actually compare here. The reason why it's just important to know even like A, for example, is because as you see here, when we did our isotope for carbon, as soon as our periodic table loads, while that's loading, there we go. It is the 6th element, okay? Perfect, so that's why we have 6 there. It means that it has 6 protons, and the superscript up there, that number above, indicates the mass, which is calculated, in this case for the isotope, is going to be protons plus neutrons. So knowing that this carbon 13 will actually have 7 neutrons. This is just extra information to really get familiar with what these isotopes mean, because isotopes are pretty much typically going to be it's the same element, but it's different amount of neutrons in them, if that makes sense. And exactly, this one will be B minus A neutrons, just like how we did up there. So overall, we have B being the atomic mass of that isotope, which is just protons plus neutrons, and that is how you would do the hyphen notation. For example, they actually use carbon 14 in this one, okay, and that is another valid isotope for carbon. In this case, this carbon here would have 8 neutrons, okay? And it's key here, the mass number is the number of protons plus the number of neutrons of that isotope. So this is correct. Alright, now let's move on to question 3 for tonight. I really like to keep them all in the same color pattern. Is salt a mixture? Okay. So, that is a very great question. Okay. So, salts in general, if I remember correctly, are, when we refer to the periodic table, are usually anions paired with the alkali metal. So alkali metal plus anion, that will give you your salt. The reason why I say this is because you'll see actually a lot of different things, or is it the halogens? We'll see how this goes. If we have, because the reason why I say this is because NaCl, and this is a salt, okay? Potassium chloride is also a salt. I think it's actually anything with chloride, which they define as salt. In fact, let me see here. Definition, chemistry definition of salt. Because we don't want to just limit this explanation to just working with NaCl, because there's different types of, I guess, salts, but you'll see they all have a certain common element to where you can say whether it's a mixture or it's going to be a compound. Chemistry definition of a salt, okay. An ionic assembly of cations and anions. Oh, wow then. So it doesn't have to be even an alkali metal. In fact, anything really can be considered a salt. That's actually good information because it still works. Cation and, so I guess I have the last part right. So that's good. So it doesn't have to be any specific type of metal. It's just alkali, well, not alkali. It doesn't have to be any specific type of metal. It can just be any cation. Okay, plus anion. So the reason why I say that is because, exactly, NaCl is a salt, KCl is a salt, Ca SO4 is also a salt. I'm trying to remember, it's SO4. Yep. Calcium sulfate, that's also salt. In fact, let me check here. Calcium sulfate salt. And people are asking if it's safe to eat. Probably not. But yeah, CaSO4, that's also salt. I can keep going on. The list becomes extensive because if we're talking about cation and anion, specifically speaking, like, you know, the metals with, so we want an ionic bond typically. I think that's a key part. We want an ionic bond because those are what form cations and anions. You're no longer sharing the electrons. What's happening is that the cation gives the electron to the anion. You'll notice that, like, for example, if you say something like, let's see, carbon dioxide, CO2, okay, this is not a salt because this is more of a, these are polar bonds in there rather than actually ionic bonds. So that's the key definition here. You need an ionic bond, okay? But exactly, the list is quite extensive because we have a lot of metals here that can contribute to being an ionic bond, and we have a lot of combination of nonmetals or anions that can be used in order to make this salt. Now, with that all being said, the thing you notice is that you have this as one of the compounds, this another compound, this another compound. The key thing though is that when you think of the sodium chloride salt, like the first example, okay, it's just going to be a, I guess, a composition of only that, okay? There's nothing else in there. And the reason why that's key is because of the fact that a mixture, okay, the definition of mixture is that it needs two or more different things floating in there, okay? So this is an example of a mixture. Think of like the air you breathe. That's a mixture of oxygen, carbon dioxide, nitrogen, and other atmospheric gases. But when you think of salt, all that's in there, well, specifically table salt, would be sodium chloride, okay? When you think of potassium chloride, like that salt, that's all that's in there. Calcium sulfate, this salt, this is all that's in there, okay? So with that being said, it's not going to look like this diagram here. It's actually just going to look like this. This would be, in a sense, your table salt. You know, you have your container, okay, where you shake out the salt, and all there is in there is a bunch of NaCl molecule pieces, okay? Nothing else. So with that being said, salt is not a mixture, okay? So the reason why I have to explain what salt is composed of is because, for example, like they can throw a lot of, I guess, basic terminology towards like, is air a mixture, is salt a mixture, is water a mixture. And so like for air, like I just said, it has different compounds in it. Salt, depending on what you're dealing with, type of salt, if they say sodium chloride, that, like table salt, that is not a mixture. Now, if they were to give you a question that said this had sodium chloride and potassium chloride in it, that would be a mixture. Now you have two different salts mixed together. That would be a mixture, and also quite unsafe to eat, I'm guessing. You don't want to eat potassium chloride. Maybe you do. But I do know that the one that's true and tested and safe is our table salt, sodium chloride. But exactly. For salts, the only way it's in the mixture is if they tell you with detail that it's composed of at least two different types of salts. Okay? So yes, let's see how we did. Common salt, table salt, is forming a sodium reaction with chlorine. Okay? And with that being said, the common salt is a compound, a type of pure substance, and not a mixture. Okay? So with that being said, it's a ionic compound because of the ionic bond I mentioned earlier. That is what table salt is. The reason why it's a compound is because if you zoomed in to one of these pieces, you'd have the chlorine part and you'd have the sodium part, okay? They're stuck together. And that's what a compound is that when you look at the molecular structure, there's two different things there. There's at least there's at least two things there, okay? Because this is like, for example, if we said like helium gas, that is an atomic element just by itself, that dot right here. This would be helium, okay? Oxygen, all right, would be two of the same dots, okay? And this is what we call a molecular element, okay? And then if we have salt, which is NaCl, all right, as it's defined in this picture down here, this is what we call a molecular compound because it's compounded of two different things. So you can still have two or more things together, but if they're the same thing, it's considered a molecular element, not a compound, okay? So with that being said, this is correct. salt is indeed not a mixture. So we're on question 4 now. Okay. All right. So we have, what is the atomic mass of silver? Okay. Now I'm actually glad we touched base on the whole atomic element versus molecular element versus molecular compound, because it'll actually help us here. Okay. Silver, okay, is known to be an atomic element, aka silver is perfectly fine, as you've seen, like things made of silver and stuff, just being by itself. Okay, it's probably like has like metallic bonds of the silver, but primarily you can think of silver just really isolating itself and being content with it. That is how silver likes to roll. Okay, purely made of just itself, specifically individual particles of silver. Now, because we know it's an atomic element, that's how we can actually now just simply refer to the periodic table, alright, and pick out the atomic mass for silver. Okay, so here it's written 107.87, and we put the units. Okay, the reason why we can write that is because exactly silver is by itself, so we don't need to multiply that atomic mass with any ratios or anything like that. We just take it straight from the periodic table, and that is going to be the atomic mass. Like I said, if it was for some reason like a molecular element, like oxygen for example, if you look at that, oxygen is O2, so whatever you saw in the periodic table, you'd multiply that by 2 to get the molar mass. Okay, and this question actually even helps you further by specifically asking for atomic mass, because when you see atomic mass, it's no longer referring even to like you wouldn't see atomic mass of a compound. That is structurally doesn't work, because when they ask for atomic mass, they're referring straight to the periodic table, and that number that's going to be at the bottom of the element box, that would be the atomic mass. Okay, so with that being said, if they were to ask, and this would be a trick question in a sense, the atomic mass of oxygen, you would not multiply by 2, it would just be what it says right there, because the fact that they're asking for the atomic mass of an oxygen atom, not an oxygen molecule. Okay, and they do have that 107.8682 grams per mole, and this is correct. So with that being said, I do want to stress that the most important part to me really is that you have to make sure you're watching what they ask for. Molar mass is not the same, well, molar mass is not always the same as atomic mass. Okay, just want to put that out there. Atomic mass from the periodic table and molar mass can require some further calculations. Now let's move on to question number 5. Wow, I'm glad I went through that whole tangent, because this is asking for the molar mass of ammonium carbonate. Okay, so first, to solve this question, we actually need to figure out what ammonium carbonate is, and this one does actually require not just some but complete memorization, because ammonium is something you have to memorize as a molecule, and carbonate is also another type of ion you have to memorize as well. So split it in half. An ammonium ion, okay, let's first remember what ammonia is. Okay, ammonia is NH3. Ammonium, okay, is an ammonia with an extra proton, so an extra hydrogen without any electrons flies in, making it have a positive charge. So we have NH4 plus. This right here is ammonium. Carbonate, okay, we have to break it down by its name. We have carbon, and we have 8 as in ATE. Okay, so this one, as I said, you kind of have to memorize. So we have carbon, okay? And the 8, because instead of it saying carbonide or something like that, or carbide, depending on how it's done, the any of 8 implies there's oxygens attached to it, okay? And how many oxygens, this part you have to memorize, okay? But I know that carbon 8 has 3 oxygens attached to it, and it also has a -2 charge, okay? So that will be the carbonate ion, all right? And also the cool thing is that if you calculate like their oxidation number, carbon will serve as a plus, well actually we don't do that first. Oxygen typically always likes to have a -2 oxidation number, so this would be -6 in total. Carbon is going to have that +4 based on periodic table, so we have +4, -6, and in total we have -2, which is the -2 charge. That's just a way of confirming that it is the 8 version, because as you notice for all the 8s like sulfate, carbonate, nitrate, you will see that the charge is actually a reflection of their oxidation numbers typically when they're actually the 8 form. And then the ites, that's when you subtract 1 oxygen, but still the same charge. I'm not going to get too much into that, only because it's asking for carbonate. So with that being said, we have 1 positive charge, 2 negative charge. To balance it out, you need to multiply the ammonium by 2, so you can have 2 positive charges. So now the formula would be NH4, 2, and then CO3. This is a molecular structure for ammonium carbonate. Now that we have that, we can actually calculate the molar mass by adding up the constituents. Remember how I said molar mass is the same thing as atomic mass? Molar mass typically is an addition of atomic masses to get the molar mass. Sometimes molar mass can be the same as atomic mass if you have just one thing. For example, molar mass and atomic mass of silver will be the same because it's just 1 silver atom. So let's see how we break this down. We will do that by this 2 subscript here. We multiply both the nitrogen and the hydrogen, so we actually have 2 nitrogen, okay, plus 8 hydrogen, okay. Then we have just 1 carbon and 3 oxygens, okay. And we go to the periodic table to get all the values we need. So we have nitrogen is 14.007, hydrogen is 1.008, carbon is 12.11, and oxygen is 15.999. Then we make these equal whatever math we need. So 2 times 14.007, that's 28.014. 8 times 1.008, 8.064. Carbon will stay the same, and 3 times 15.999, we have 47.997. So these 4 are all going to be added together, okay, and now plus that 12.011, and we get 96.086 grams per mole. And this right here would be your molar mass of ammonium carbonate. Let's see how we did. Yep, we got that, NH42CO3, and then we're going to add it together. Yep, and they get 96.11. So theirs is different because as I've said this in other videos, depending on your periodic table and how they round there, and that's the one you want to use. So you might even get a different answer from me, but you always want to make sure that you're referring to the periodic table given to you by your instructor, because if they're really retentive on, you know, having the exact value, you can only get that exact value by using the numbers that they gave to you, okay? So I would advise not looking up the numbers online if you've already been given a periodic table. If you have not been given a periodic table, then go with online, but just make sure you're always referring to the same periodic table just to keep your answers consistent. So with that being said, moving on to question 6. Now, this question is asking, what intermolecular forces are present between ethanol and methanol? Okay, so with that being said, give me a second to make sure that we can get any sounds. Ethanol and methanol, right? Let me just write the question down. Intermolecular forces present between ethanol and methanol. So another example of things that you unfortunately have to memorize, but let's actually break this down by their prefix. So let's start with methanol, which is actually the prefix of methane. So methane is CH4, okay, because that is one carbon in that hydrogen group, because these are hydrocarbons that I'm listing out. And methanol is when you have an hydroxide group added and you replace it with one of the hydrogens. So you have CH3OH, okay, which kind of look like this if it was drawn out, okay, because that carbon bond is there. Ethane, okay, is now 2 carbons, so now you have C2H8, I believe, yeah, well, C2H6, that should be better, yeah, times 2 plus 2, there we go, C2H6, and now same process of ethanol, you would replace that with a hydroxide group, so you have C2H5OH, and you kind of look like this. Let me do that better. Okay, so that's methanol and ethanol. Okay, and now they're asking for the intermolecular forces present between ethanol and methanol. So what are the list of intermolecular forces that are possible? We have the London dispersion force, okay, which is present in everything. We have, if I remember correctly, polar or dipole, there we go, pole bonds. We also have hydrogen bonds, and we have ionic bonds as the last one. So, or ionic forces in a sense. This would be how it goes from weakest to strongest. Okay? So, with that being said, we'll actually go through and list out what we do have, okay? So between methane and ethane, I mean methanol and ethanol, think of these two floating near each other and everything. So with that being said, we're going to highlight them. So London dispersion, as I said, every single type of molecules have this force that attract each other. It is the weakest force. It's kind of like a gravitational field, very weak, to where molecules that are floating around, they'll like to attract each other just slightly. So that is a check for that. That definitely has that. Dipole. For this one, you kind of have to look closer into your intermolecular force, like the bonds there. And you can actually see here, right, for the dipole, you have a carbon attached to an oxygen. Same thing here, carbon attached to an oxygen. So the way you figure out dipole is by looking at the periodic table, the electronegativity, draw in a different color, the electronegativity, and seeing if your molecule is polar, has a polar and a polar, has a positive and negative pseudo charge. Okay, so if you compare carbon and oxygen, so the cutoff for polarity is 0.4 difference of electronegativity. Oxygen is 3.44, carbon is 2.55, so 3.44 minus 2.55 we have 0.89 difference. So with that being said, actually, this is going to have a positive, well, not charge, positive, I guess, polarity, and this is going to have a negative on the oxygen. Same with here, positive and negative, okay? So with that being said, if methanol and ethanol were floating, like a bunch of methanol, ethanol, you'll typically see the carbon be attracted to the oxygen, okay? Because that's kind of like their that's how they will be structured, because the carbon will serve as kind of like the positive polar end, and the oxygen will serve as a negative polar end. So with that being said, it does have dipole-dipole bond as well, so you can check that off. And now hydrogen bonds. You're probably wondering why I skipped over the oxygen and the hydrogen, because that could technically count as polarity, but this is actually one of the hydrogen bonds. Okay, there's 3 types between hydrogen and oxygen, as here. Hydrogen and nitrogen, that's another hydrogen bond, and hydrogen and fluorine. Okay, NOF is usually the acronyms they use. So because we actually have hydrogen bonds as well, when methanol and ethanol float near each other, you typically see the oxygen of one try to bond the oxygen one try to bond the hydrogen of the other, as it kind of formed that weird in a sense hydrogen bond. You see this OH here, so this O, we kind of want to attack that H, okay, because that's just typically how oxygen or any other of the 3 I mentioned, nitrogen and fluorine, like to roll, is that when they're in the presence of hydrogens, they just like to grab. And then you'll see as this one's trying to grab that, maybe another ethanol molecule is trying to grab their hydrogen. So you have a lot of that hydrogen bond interaction there as well, okay? So with that being said, this is what we have so far. Ionic specifically says between a metal and a non-metal. When I've written down the names for methanol and ethanol, do you see any metals in there? Unfortunately, no. We have hydrogen, which is a non-metal, carbon, a non-metal, and oxygen, also non-metal. So it does not have ionic bonds. So the 3 forces you'll see there are London dispersion, dipole-dipole, and hydrogen bonds between ethanol and methanol, okay? And typically, maybe not always the case, but typically if you have a hydrogen bond, you most likely have dipole-dipole, because whatever the oxygen is attached to is on the other end, or nitrogen or fluorine, they're forming that dipole disparity, where one side is a little bit more positive and the other side is more negative. So we have the pictures correct for ethanol and methanol, so that's good. They talk about the van der Waals forces, which is the London dispersion, okay? And the other one is hydrogen bonding, which is more dominant than the first one. And unfortunately did not mention there is also dipole, and it's important to make the distinction, because for questions like these, typically if you miss one part, you still miss the whole question, because that is dipole still play a very important role in terms of the orientation of the methanol and ethanol in the solution as well. Because just because a hydrogen bond is stronger and they prefer that, you have to consider, like, you know, the spacing and whether they can actually fit there, like stereochemically, which is the shape and everything. So all of these things do play an effect as well. So that would mean this is unfortunately incorrect. And yeah, so that's something I remember. At least when you end up at hydrogen bonds, you typically would have the other 2 prior as well. So now number 7, what is the difference between mixture and compound? I do believe we touched this a little bit, but we can now further delve into this. Sorry, the difference between mixture and compound, okay? So another way to explain this question actually is kind of like the, how do I put this? Actually, no, that's not a good way to explain it. I was going to do the whole squares and rectangles thing, but you'll see that a compound doesn't always have to be a mixture, and vice versa. Okay, if I had one single H2O molecule, okay, as I said earlier, this would be a compound, a molecular compound, because it's composed of different things, okay, right? But this wouldn't be a mixture. Although it's quite impossible to have one single molecule of water. If that was the case, it wouldn't be a mixture, okay? Because of the fact that the key thing for mixture is now you're no longer dealing with, I guess, one molecule. You're dealing with multiple molecules. A mixture needs in fact, that's actually a perfect way to put it. Mixture needs multiple, I wouldn't even say molecules, molecular, yeah, actually no, molecules is a perfect word. Molecules, okay, that is what a mixture needs. And a compound, actually, this is a part that's kind of cool in terms of how you can relate them. Compound needs multiple atoms. This right here is a distinction between compounds and mixtures. What do I mean by this? This water compound has multiple atoms, but not multiple molecules. This would be a compound of H2O, but not a mix. Well, not a mixture. And actually, I'll specify here another difference that needs multiple. Let me move this, because this is where it gets a little bit more wonky. Is that it needs multiple different molecules, okay? And that is very important, because that is for compounds. It doesn't really, molecular compound needs multiple different atoms, so they're actually quite related. And the reason why I wrote it like that is because you hear of molecular compounds and molecular elements, as I discussed earlier, molecular elements being composed of the same type of atom. Okay, so like O2 is 2 of oxygen. A compound, molecular compound now, instead of molecular elements, is like this H2O, the water molecule. Okay, that is multiple different atoms. A compound would also be like NaCl, as we discussed earlier, because just one sodium, one chloride, okay? This is also a compound because it's multiple different atoms. Now, as we're saying, back to the whole relation to mixture, if I had 2 water molecules in the same space, okay, which is also very hard to do, but still, for this example, this is still not a mixture, okay? Because it's multiple of the same molecule. But if I were to throw in a sodium chloride, okay, alright, like that, into that same, I guess, bin, this is now a mixture because it has multiple different molecules. Even if I were to remove one of the water, this is still a mixture. It's a 50-50 mix, half NaCl, half H2O. But exactly, that's the key difference there between mixtures and compounds. Compounds deal on an atomic level, mixtures deal on a molecular level. So it's a step up, okay? So compounds atomic level, mixtures molecular level, okay? And what differs from each other is how the elements constitution of the samples are contained. Compounds are materials that contain both elements, bonded elements and molecules, exactly. So it's atomic level in terms of bonds, and mixtures don't involve bonding, okay? It's now on a molecular level. These consist of different atoms or molecules in a specific space. they will share some in terms of hydrogen force. In fact, that would be actually a better name. Some hydrogen bonds, like in this previous question, they will share some different types of forces in terms of the when they interact with each other, okay, like when they float by, but it's not like actual strong bonds formed unless, you know, there's a bond breaking and another bond forming. So with that all being said, exactly, mixtures are on a molecular level, so these molecules are not bonded to each other, and compounds are dealing on an atomic level where the atoms are bonded to each other. Okay, that is a key difference of mixture and compounds. Okay, this is correct nonetheless, because it does talk about the bonds for compounds and a lack of bonds for mixtures. So let's move on to question 8. All right, how do you calculate KSP from molar solubility? So this question is a bit tricky, that requires multiple steps, but once we get it down, it's actually not too complicated. Okay, all right, so if in order to first get KSP, we need to first think of a random molecule. Okay, that's what we're gonna work with. Okay, for the formula, we have A, X, B, Y. Okay, so it has different subscripts, and this dissociates. Well, in terms of that, we have to use this line because it's not a complete dissociation. That's what the KSP is for. We have XA plus, whoops, forgot to put it lowercase, XA plus YB. Okay, that in a sense would be your formula you're working with. Okay, and it would have, like, you know, the charges. It would be plus because it's a cation and an anion. This right here would be an anion, would be the A minus. I mean, oops, not B. It would be Y minus and X minus, Y plus and X minus. So the way it balanced out is pretty much saying that these charges would balance out in total to make sure that we still have a net charge of 0 from the original thing we started with. So overall though, that is the formula we're working with. Now, the formula for KSP is that because this is typically solid, we disregard the product because usually it's products over reactants. But to calculate KSP, because the reactants, like, it's usually just a solid there, we don't factor that in. So we have, okay, so ignoring really the charge, well, can't really ignore the charge, but we're gonna have A, the Y plus, okay, times the B X plus. Okay, so that's just a charge, but you have to put it to the power of these coefficients. So it's going to be to the power of X and to the power of Y. Okay, so with that being said, we now have, in a sense, a breakdown. And the reason why we get to put it to the power of is because that's what the coefficient does. It's not a direct multiplication. You're increasing it by that power. Okay, so now when they give you molar solubility, right, it's pretty much an amount of the AXBY that dissolved. Okay, so they're like, the molar solubility was 0.13 moles per liter. That's what they give you. Okay, so with that being said, right, if you wanted to figure out how much of the A and the B was produced, you would actually break it down accordingly. Okay, you would have AXBY, for example, and you will see here, to convert them, be 1 mole based on this formula up there of AXBY is equal to whatever that X is in front, X moles. In fact, I'll make this no, I'll keep it lower. but just don't lose, okay? It would equal X moles, that's a coefficient, right, of AY plus. And the same thing, actually, it would be, so whatever you have, you multiply it by that coefficient, and that would be what you get. And then same thing, actually, if it was now for the B, it'd be the Y moles, the coefficient there of BX minus per 1 mole of AX BY. Why am I saying all this? Okay, it's because now if we used AX BY in a sense was C, because we just got like a value for it, right? So AX BY is equal to C, right? We can actually now use this, okay, these coefficients, to replace that to form a better direct KSP. So now what we have, okay, is that the KSP formula is that as we replace this number, this value with just C, right, you will see that it would be X times C, if that makes sense, and this would be Y times C instead of the A and B. So then the KSP value for that solid or whatever it is, it'd be X times C, okay, with that, you know, we don't really have to put the charge there, but you can put the charge there just to be able to make sure that you're understanding it. But for them, I'm going to leave the charge out. We just know that whatever the amount is, it's going to be times that coefficient there, but you cannot forget your power. So X times C to the power of X times Y times C to the power of Y. That would be what you would use to calculate your KSP. What does this mean? It means that if you're given the question, like we said, it was 0.13 moles of whatever, and it broke down to 2 moles of A and 1 mole of B, you would have, we plugged it in, right? It'd be 2 times 0.13 to the power of 2 times 1 times 0.13 to the power of 1, and you would get 2 times 0.13 squared times 0.13, because that's all of this is here. Your KSP value, made up one for this one, would actually be 0.0088. Okay, that, in a sense, this formula here really is how you calculate your KSP from molar solubility, because your molar solubility really is that C. C is your molar solubility, the value they give you in terms of like moles per liter. All right, so that would be, this equation would be how you solve it based on the equation I've given you here. So with that being said, let's see how we did. Exactly, we did convert it correctly. A times S is pretty much like what we did with the X times C. So then when you replace it accordingly, you have X times CX, Y times C, Y, and that is what you use to calculate molar solubility, and this is correct. So let's move on now to question number 9. We have, for question 9, what is a molar mass, a keyword molar mass of helium? Okay, so now, just as we did with the other question, we first have to figure out what helium prefers to be. Is helium, let me just remember. Is helium going to be an atomic element, a molecular element, or a molecular compound? So for this, once again, unfortunately, you kind of have to memorize it to be able to navigate it, okay? So with that being said though, okay, if we look at the periodic table, you can get some hints of what helium would like to be. They just say helium, right? So we know it's not a molecular compound because it's only composed of helium. We're trying to decide now if it's going to be a molecular element, so like multiples of helium, or just an atomic element where it's helium by itself. Helium is a gas, but the key thing is that it's a noble gas. Okay, noble gases don't care about having bonds with anything else. They're perfectly content with what they are, kind of like those metals we're talking about, like silver earlier. So with that being said, helium, think about it, it's just going to be an atom by itself. And as we discussed earlier, if you have an atom by yourself, your molar mass is going to be the same as your atomic mass. So if we look straight to the periodic table and we saw the atomic mass, helium is 4.0026, okay? And we put our units because that actually would be the molar mass for helium, okay? So with that being said, we have 4.003 grams per mole, which is also correct based on their periodic table. But exactly, that's all you have to do for this question. But the key thing is identifying that it's an atomic element, because although it's a gas, it is a noble gas, and noble gases are completely fine by themselves. They don't need any bonds with themselves to be able to even, I guess, become more stable, because they're already perfectly stable as they are. So now question 10, okay. This one's asking, is IF2 polar or non-polar? IF2 minus polar or non-polar. So this one's a little bit tricky, right? Because we need to see how to first draw out its Lewis structure. And then from there we'll see whether it's actually polar or not. Okay? So with that being said, we're going to first figure out how many electrons, well, in the valence shell for iodine, fluorine here. Okay, so we can do it two ways. We can just see if it's on the periodic table. They're both halogens, so they would have 7 each. Or we can also do the electron configuration, which I've been doing for like every single question that I could. So we have start at the most recent krypton, the most recent noble gas, then we go on to the actual rest of it. Okay, so we have 4d10, because I know that you have to pass through D levels first, so I'm just going to label that first. And then we have 5s2, and then we have 5p5. So looking at the 5 specifically, you will see that 2 plus 5 equals 7, aka how iodine has 7 electrons. Okay, and now fluorine, say, starts out at helium, because that's the most recent one, or the one right before it, and then we have 2s2, 2p5 as well. Okay, and the reason why I'm saying this is because if you count on the periodic table, the p row is actually starting from boron to neon. Well, column 13 through 18. The D subshell starts from column 3 through 12. You can actually count one by one, and you'll see how I actually got these numbers when you're counting through them. And also the S column is 1 and 2. So with that being said, still 7 as well. But exactly, if you're not comfortable with that, just use the rule of where it is on the periodic table. It's a halogen, column 17, so 7 electrons. That can also be used. Okay, but this one has times 2 because it's IF2. So it's an iodine fluoride ion, iodine difluoride ion, if that's probably going to be the name of it. Okay, so it has 14 here plus 7, and now we see the key thing here. There's an extra electron, hence shown by the negative. When there's a negative there, it's another electron added because electrons are negative. If it's positive, it means it was taken away. So 7 plus 14 plus 1. So in total, we have 22 electrons. Okay, now let's go and draw out the actual Lewis structure. We'll put iodine in the middle, okay, because we are working with double fluorine, so it only makes sense that the iodine will be in the middle because that's a different one. And then we fill in the rest of the electrons. So fluorine likes to have 7, so it'll be sharing 1 right now, 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7. Now iodine, 2, 3, whoops, sorry, 2, 3, 4, 5, 6, 7. So what just happened here? Iodine actually does not care about the octet rule in this case. It will willingly have 10 electrons, I guess, around it because it's still stable there. In fact, if you were to get the electron number for each one, you will see, starting with iodine, okay, it has typically wants 7 valence electrons. So you subtract how many lone pairs it has, so lone electrons. It has 6 lone electrons, and how many is it sharing? Next, let me just make sure. Yep, 2, 4, 6. How many is it sharing? It's sharing 4. Oh, that's interesting. Maybe I skipped a part. Exactly. So right now, fluorine is content. Let's see here. Iodine just wants. Oh, well, that's why I miscounted. Iodine is going to be. Typically, it has 1, 2, 3, 4, 5 more because it's sharing 2. So I miscounted there. It's gonna have 1, 2, 3, 4, 5 more. Okay, but because of the +1, that's gonna be the 6 electron here. Okay, and now it makes more sense how iodine was breaking the octet rule, is because that +1 electron just makes it stable there, and you actually see now how iodine has the negative charge. So 7 minus 6 valence electrons plus 4 over 2 because it's sharing 4. Okay, I mean, well, 6 lone electrons, and we get 6 plus 2 is 8, so minus 1. So that's how iodine actually has this -1 charge. The fluorines will hopefully be neutral, and you can do the math, still 6 as well, but each side is really only sharing 2. So 6 plus 1 does equal 7, which makes this 0 actually. So based on this, you can actually see that the iodine is where the negative charge will be kept. Now it's asking if it's polar or non-polar. So with that being said, this is where it's a little bit tricky because you have to really visualize this. Let's start with the electron, not the electron number. We want the electron pair number, okay? Electron pair number of iodine. And for that, we figure out how many, I guess, pairs / things it has attached to it. Okay, we have here 2, well, not 2, 1, 2, 3, 4, 5. So electron pair number for iodine is going to be 5, okay? And I don't remember the shape off the top of my head, but we actually refer to our, you know, our Vesper theory, okay? That's what we would use to be able to figure that out. And in fact, more so, we have to also find out its molecular geometry as well by now comparing how many bonds it has versus how many lone pairs. So it has 2 of the 5 bonds, 2 of them, I mean of the 5 things attached to it, 2 of them are bonds, 3 of them are lone pairs. So let's go over to our Vesper table here. It's all the way here for the electron groups 5, and we have this 2. So all of them actually are the name in general for the electron geometry. Electron pair geometry is trigonal bipyramidal. Okay. And now when you have 2 and 3, we have, it even shows a picture actually of it, it's going to appear linear. Alright. And the reason being is that if I were to draw it out with the electrons, right, it kind of look like this, okay? The iodines, the fluorines are up here, and now the lone pairs form like a perfect ring around it, like in this axis. Like if this was the planes, in fact, well, actually I'm gonna leave that picture here. All right, think of the electrons on the x-axis and the fluorines on the y-axis. Okay, you still have the 6 electrons there, the 3 lone pairs, but that's what it would look like at a glance. And now this is the part that becomes very specific, because you have, like, in a sense, an x and y axis, and they're all electrons just pulling at each other perfectly. All the, I guess, the vectors for the x direction are canceled out. So all you have left is to look at the y axis, okay? And the y-axis, you have a fluorine on one end and another exact fluorine on the other. So the vectors for the y-axis also cancel out. So in total, actually, for the vectors, you have no net movement, okay, or net charge distribution, because the x cancel out and the y cancels out. So with that being said, even though it may not look like it, okay, IF2 is a non-polar molecule, and you can really only figure this out by drawing its well, actually by knowing its molecular geometry, because if you look at this, you will think that, oh wait, the electrons must be moving, or at least pulling in a certain direction. But as you see, the electrons are only competing with themselves based on this picture, okay? So that's why they cancel each other out. Electrons will be electrons. There's no winner from there. So all that's left on each opposite end are the 2 fluorines, and you can see for sure that those two will cancel each other out. Hence why we end up with a linear shape. So that being said, yep, it's non-polar. They draw the Lewis structure, and then I hope they mentioned the geometry. They do have symmetrical arrangement, okay, and therefore it's non-polar, but it's actually, I would say this is correct, but like I said, it's key to know the molecular geometry, just so that way you can actually visualize how the molecule is non-polar. So with that being said, let's move on to question number, we just solved 10, so 11. It's important to always keep yourself hydrated, so with that, just a slight little water break, okay? All right. So, with that being said, this next question is asking, what is the oxidation state of each element in COH2? State of each element in COH2. So, for this one, unfortunately, these are parts you have to memorize. Not for the carbon, luckily, but for the oxygen and hydrogens, okay? Oxygens, typically, in every scenario, okay, will have an oxidation state. So, these are the 2 rules you really have to keep to heart. State of, oxygen, oxidation state. There we go. State, okay, typically likes to be -2. Hydrogen, oxidation state, okay, is gonna be typically +1, okay? The only exception for where hydrogen is minus, I know there's an example where hydrogen is a minus, but let's start with the oxygen one. So the only where oxygen is not -2, okay, it'll be -1, is when we have H2O2, okay? In this case specifically, oxygen is -1 and hydrogen is still +1, okay? Now for the hydrogen, I do believe it's like NaH or something like that. When it's bonded with certain types of metals, the hydrogen then likes to be, sorry about that, the hydrogen there likes to be -1, while the metal will be +1. Specifically, I do believe it's from like either the first rule, so the non-transition metals, I think that's where the rule applies to. That's where the hydrogen will then serve as the negative. Okay, these are the exceptions here. okay, but typically it's going to be -2 plus 1, okay. So with that being said, when we look at this, we don't have any metals here, so that's good, and we have COH2. We do not have that peroxide. You need specifically that peroxide type of combination for that rule to apply. So with all that being said, we have -2 because only one of them. Hydrogen, okay, is going to be +1, okay, but there's 2 of them, and what I like to do is I like to write the total at the top, so +2. So if we already have a -2 and a +2 there, the oxidation state of that carbon, because this is a neutral element, a neutral compound, it would have to be 0, because +2 -2 would be 0. So that means this carbon has an oxidation state of 0. So let's write it out. We have carbon is 0, oxygen is -2, and hydrogen, okay, remember referring just to the individual ones, is +1, okay. So like I said, this is going to be the individual that I like to do down here. This is just the way I like to do it, and this is going to be the total at the top, okay. So what you usually do is the individual times the script or whatever it is, the subscript, and then that's how you get the total at the top. Alright, and this should equal the either 0 if it indicates that the molecule is a net charge of 0, or whatever ion amount. So like if you have like sulfate, for example, right, that's 2-, you want to make sure the oxidation state adds up to where you end up with a 2-, okay. So that being said, let's see how we did. The important rules, they do break down a lot. The oxygen is just make sure, yep, is usually -2, except for peroxide, which is what we have there, where it's -1. Nitrogen is typically, it can change based on what it's attached to. The sum of the oxidation numbers is equal to the charge of the ion. So in this case, the charge was 0, and the oxidation number of hydrogen is +1, except for the explanation of what I did there, where you have hydrogen bonded with like metals, okay. Therefore, we let the oxidation number x the oxidation number of the carbon atom. We don't know what carbon is. That's typically what you'd see there, is that you usually have givens. You have I guess elements that you do know about, and then you have to kind of fill in the blanks with elements you don't know about based on the charge of that molecule. So as it shows here, exactly -2 plus 2 is equal to 0. So carbon is 0, oxygen -2, hydrogen +1. So this is correct as well. Let's move on now to question number 12. Okay, so we have, what is the correct name for the binary ionic compound Cu2S? So binary just means it's composed of 2 things, just so you don't get confused by that. So correct name for Cu2S. So there's a little bit of a trick here, okay? So the first thing we have to do is I actually prefer to actually go by the anion here. The reason being is that copper is a transition metal. So that one is kind of always in the air of what you will decide in terms of like the actual charge of it is. So we'll go with the givens, kind of like the whole oxidation number thing, because sulfur is, on the 16th column. So it typically likes to have 6 valence electrons. Okay, so usually to get full, you just like to add 2 more. So that's why it'd be for a sulfur ion, you typically have that sulfur 2-, because then it gets 2 more for it to be complete, and that would be a sulfide ion. So with that being said, we have something like this, okay, because it's just the element by itself as the anion, you have the name sulfur, you drop the ending, okay, and you add high De. This is the sulfide ion. You can also see it once again in the electron configuration. Yep, we're going to do that as well. Start with neon because it's the most recent noble gas, and then you keep going. It'll be 3s2, 3p4. As you see here, it also has, you know, 6 valence electrons. So instead of getting rid of all these 6, it'd rather just change that little part and add 2 more, so it becomes like the noble gas argon. So this would be the electron configuration of that sulfide ion. Point being, overall, this is sulfide, S2 minus. Okay, but now we know that copper had to have come with 2 of itself to match that 2 minus charge. So in order to figure out the charge of each copper, okay, we need to divide the 2 minus charge. Okay, well, technically 2 plus, because that's what the copper is going to have to be able to balance that out. You need 2 plus to balance the 2 minus. We're going to divide that by the amount of coppers it says, so 2. So that means each copper had to have a charge of plus 1. So that would be the copper charge. Now, when it comes to transition metals, there's a specific way to name these, okay? You have to put in parentheses what type of copper it is, hence the charge. When it's, you know, I'll just list of numbers, but if it has like 1 electron being lost, it'd be the copper 1, and it would have the 1 in parentheses, but as a what's that called again? That type of numbering, Roman numeral. There we go. Roman numeral 1. If it gave up 2 electrons, it would have the Roman symbol for 2 right there. Okay, but that's what you put in the parentheses. So for this, you would still have to write out the name copper. Okay, and now the parentheses, you would have just the Roman numeral for 1, and then you would just add the name for sulfide. And this right here is going to be the correct name for copper. It still will be called copper sulfide or copper 1 sulfide, but that'll be the correct name for it. Okay, so see what we have here. Luckily for us, we have B, because A, copper sulfide, that's not specific enough, so that wouldn't fly. B, we have that copper 1 sulfide. C, copper 2 sulfide. That one, if you probably guessed it, if it was 2 electrons being given away, you'd actually end up with this, just CUS, because now you have the positive 2 and the negative 2 cancel each other out. So this is what copper 2 sulfide look like. And D, there is a correct response, so that's not it. So the answer is still going to be B. Okay. So with that being said, let's see how we did. Yep, copper 1 sulfide. And we were able to show how we got there. Let's move on to the next question. Question number 13. Alright, so now we have this question 13. It's asking us how many orbitals are in n equals 4. So, orbitals in n equals 4. Okay? So, for this, you kind of have to break down into the orbital notation. That's at least how I think of it. Okay? So, if n equals 4, right, that means L has a potential to equal 0, 1, 2, or 3. Because the way it works is that whatever n is, L, okay, L is equal to n minus 1, as in the max value for L. So that's what we have here, okay? And now, to specify what these actually mean is that each one is going to be, how do I put this, representative of the S, P, D, and F shell. So we have S, P, D, and F, okay? And now each type of, I guess, subshell has a certain amount of orbitals. If you remember the orbital notation, okay? S as you see on the periodic table, can only fit 2 electrons because it only has 1 orbital. So this is just 1 orbital, okay? And in fact, if you can actually see this by breaking it down in terms of the ml, okay? That's the next value you'd use. So for the S shell, right, you'd have it's just a positive and negative values of whatever number you had there. So everything included. So this one just be 0. This P breaks down to, you know, -1. In fact, I'll just do this to make it a little bit easier to see. -1, 0, and 1. The D shell, because it's 2, is going to be -2, -1, 0, 1, 2. And the F is going to be -3, -2, -1, 0, 1, 2, 3. And now, as I said, 2 electrons can go into each. So 2 electrons will be quote unquote in that 0 for S, and there'll be 2 electrons each for every single other orbital. Okay? So it's safe to say what we can do is count how many orbitals we have. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right. So with that being said, that's actually going to be our answer. Okay. There's a cool way to do this to where whatever value for n, you can actually just square it. So the number of orbitals is equal to n squared. But these are the orbitals that unfortunately we don't really talk about. When you start getting unfortunately past like 5 and up, for example, when you pass 4, we don't really discuss the type of orbital where L is equal to 4. We usually discuss these ones, 0 through 3. But exactly, that's why I like to count it out like that. And you would have a total here, okay, of 16 orbitals, as we were able to count out. So that being said, see how we did. Okay, so normal orbitals, yep, n squared, and we actually broke it down, and we see here that the ml is 0 for L equals 1, -1, 0, and 1, and we did that exactly. And when you count it out, we have 16 orbitals. Okay, all right. So with that being said, let's move on now to the next question, number 14. Okay, so we have, what is the Lewis structure of XeH4? Okay, so for this, actually, we just have to break it down in regards to how many electrons it has. So let's start now with hydrogen. If we were to draw in terms of the electron configuration, you just see it's well, actually there's no noble gas force, just 1s1. Hence, that's how it has, well, 1 electron. Okay, and xenon, okay, would have, if we start from krypton, for example, it'd be krypton, and then you'd go through that D subshell, and that would be 4d10. So as you can see, xenon is quite close to the iodine, because then it'd be 5s2, 5p6. Okay, and from this you can actually tell that has 8 valence electrons. Okay, so now if we have xenon tetrahydrogen, or tetrahydride, that's a xenon tetrahydride, it's probably the best thing I can think of. It would actually be drawn like this. Okay, so we have 1 electron times 4, so that would be 4 plus 8. We need 12 electrons total. Alright, so let's get to drawing it. We have the xenon in the middle. That's the only individual one, like different one. And it's now sharing 4 of its 8 electrons with hydrogen. So now it still has 4 electrons left in terms of so it can form 2 lone pairs. So this right here, actually, just simply that, would be the Lewis structure of xenon tetrahydride. Okay, and now let's see how we did. Yep, that is correct. And if they're asking for the electron geometry, as you can see here, xenon would have 6, I guess, electron pairs, so it would be 6, and that would now break down to, I believe that's like octahedral or something like that. Okay, and that breaks down to having, as you can see here, 4 bonds and 2 lone pairs. So the specific name for it, that one I definitely don't know. You go down to this table here, 6 octahedral, yep, 4 bonds, 2 lone pairs, it's square planar. So it kind of looks like that, okay? So kind of like the same thing where you have the x and the y-axis, okay? The y-axis being your electrons and the x-axis being your hydrogens. This would also be considered a non-polar molecule because the x and y components would cancel each other out. Okay, so let's move on to question number 15. All right, so this one's asking us to supply the curved arrows, oh I wish you couldn't see that, to the reactants to indicate movement. So apply curved arrows to reactants to indicate movement of electrons in reaction. Okay, so with that being said, we have this formula here, NH3 plus HCl, okay, turns into NH4 plus Cl minus. Okay, so first we just have to do a quick glance at this all balanced equation, which it is, and then what we need to do actually is draw out the molecules for each to kind of see what's going on here. So we have NH3, right? Whoops. So we have a nitrogen with a double bond here, and we have 3 H's. Okay, and then we have HCl, which is bonded like this. Okay, right? And now we want it to turn into the NH4 okay, and we want to also have the Cl minus, okay, and it's NH4 plus. All right, so with that being said, NH4 plus and Cl minus, NH4 plus, how would this happen? So with this you have to watch really closely. Okay, so nitrogen has 1 lone pair, okay, and chlorine is turned into an ion with 4 lone pairs. So from 3 lone pairs to 4 lone pairs, meaning that this bond here, right, starting with the chlorine, has to go from the hydrogen to just, as in from being shared to just being hogged by the chlorine. Okay, that's just what's going to happen here. So in a sense, chlorine says, sucks to be you, hydrogen, I'm taking your electrons, the electrons we were sharing, and it's all mine now. So instead, we do have a hydrogen technically, but in reality it's really just a proton, because hydrogen has a atomic weight of like around 1, which in case it's 1 proton, and typically only has 1 electron, but that's what it was sharing with the chlorine. So when chlorine takes all that, the 2 electrons that they were sharing, hydrogen is literally just left with just a proton. But nitrogen is like, hey, you know what? I can actually make up for that. I have 2 electrons here that I can share with you, hydrogen. So the nitrogen is going to actually bond directly with the hydrogen, okay? And in fact, the way I actually explained it would actually be the backwards way it goes, okay? The nitrogen is most likely actually the way the order goes, because you want to actually, in a sense, kind of be shifting. You don't go, actually I'll just explain it and you'll see my logic here. The nitrogen actually would first go towards that hydrogen and be like, hey, I'm going to share these bonds with you. And hydrogen's like, yeah, sure. Also because nitrogen, hydrogen, those are actually considered like a type of hydrogen bond. So exactly, nitrogen is like, hey, I'm going to share this with you. Hydrogen's like, yeah, sure. Nitrogen tells hydrogen to ditch the chlorine. Hydrogen does so the chlorine's like, okay, whatever, I'll keep the electrons. So with that being said, that's the type of attack that happens, because as you can see here now, if I circle this, I can do better than that. That is the new hydrogen there, and you know, I'll circle that as well to just indicate that. So you see that bond. In fact, let me actually do this, because this bond here technically is still going to be the blue, oops, the blue bond here, okay? And these 2 electrons are actually going to be the green electrons that are forming that bond there. Just that way you can actually at least keep up with the color coordination, okay? So that's how the nitrogen attacks the hydrogen, and then chlorine keeps its bonds, and that's how we get the chloride ion, and that's how we get this ammonium. Okay, so with that being said, yep, I know you probably saw the picture already, but yes, this is indeed correct. That is how they would attach to each other. Now, question number 16, okay? This question is asking, is AgNO3 soluble in water? Okay, so for this actually, these are unfortunately things you kind of have to memorize. There's a giant solubility sheet, but the biggest hint I will tell you here is that most, if not all things, combine with nitrate, which is what this ion is. This is a nitrate ion. Okay, that is NO3 minus. Most things combined with the nitrate ion are going to be soluble in water. That is really the trick to this question. Some salts are insoluble in water. They just really have a really low, as we discussed earlier, KSP, which indicates its solubility. But exactly, if you're any metal really combined with nitrate, you're most likely, if not, going to be soluble. Okay, so actually, if we even search here, actually, nitrates not soluble. Which nitrates are not soluble? What do we get? Salts containing nitrate ions and generally soluble. Yeah. In fact, they literally can't give us an example of something that's not soluble with nitrate. In fact, I'm going to actually expand this page here. Go down over to the NO3 part. Yep. They can't literally think of anything that would make it insoluble when it's with a nitrate. So I guess that's something you have to memorize, but that would be your biggest hint. If you see a nitrate ion, it's going to be soluble. So with that being said, that is actually what you get here. AgNO3 is quote unquote an exception, because as you'd actually find out, silver is typically, like silver compounds are typically insoluble, but exactly, nitrates, like, I don't care what you are as a metal, you're going to dissolve in water. So that's why I like to memorize, at least with the nitrate end. If it's not nitrate, then you kind of have to start deciding based on what the cation is. So exactly, silver is typically insoluble in most things. So if you have like silver chloride, as they do mention here, where is it? Yep, silver chloride is insoluble. So those are examples of some salts that are insoluble in water. But exactly, when it comes to nitrate, nitrate rules all, and says, I frankly don't care what you are as a cation, you're going to dissolve in water, and that's that. With that being said, let's move on to question number 17. Actually, let's actually add that as soluble. Just a way to add. Let's finish that question. Okay. So now question 17. What is the name of SO42 minus? I wish you couldn't see that. And I'm going to actually rank that as wrong, because you always got to add one important part, which I'll show you. Name of SO42 minus. Okay. So, as discussed earlier, I think we actually had a sulfate earlier, so it should be relatively familiar. We have the sulfur part, okay, and because it has a certain amount of bonds of oxygens, it's a different ending, okay, so it's sulf something, okay. Now, with that being said, as we do the whole electron number of it, okay, the oxidation number, remember that oxygen likes to typically be 2 minus, okay. So with that being said, it has a whole 8 minus, okay. And sulfur, okay, based on this number that it has a 2 minus total, it has to be a plus 6, okay. And if you actually look in the periodic table, right, sulfur is on the 16th column, all right. I mean, it has 6 valence electrons to give. In fact, usually likes to, as we said, just take 2 more and become like argon, but because oxygen is like pretty much a bully in this case, sulfur's like, fine, I'm gonna give up literally 6 whole electrons to become like neon. So sulfur has a plus 6 charge. Why am I mentioning this? Because of the fact that, as I mentioned, typically 8s are the ones that make sense when you do the oxidation number. So this one actually makes sense because sulfur actually does have 6 electrons to give away. So with this will actually be a sulf 8, okay. That is a name, right? But we're not done yet. Why? Because this is a 2 minus. Anything with the charge is no longer just a compound, it becomes an ion. So the real name, the full name of this is that this is a sulfate ion, okay. That is a name that we have here. All right. So with that being said, S42 minus is composed of sulfur and oxygen. Yep. And the compound is conventionally known as sulfate ion. Fate ion is the whole name because of charge. Okay. And I would just simply mark this as incorrect. So, because you cannot forget the ion part. The charge is not there just to be gawked at, unfortunately. It actually needs to be factored in. So with that being said, let's move on to question number 18. What is the electron geometry of ClO3 minus? So this will be like a chlorine trioxide ion. And that's the best thing I can think of. Or actually, what am I doing? This is ClO3. This would be a chlorate ion. Yes. In fact, let's double check. Let's use the same trick. Chlorine. Let's go to the periodic table. Let's, well, use the, as we're using electron geometry, I know I didn't do it for the last question, but it's always good to just practice. We have helium for chlorine, well, helium for oxygen at least. 2s2, 2p4. That's going to be 6 electrons. And now chlorine, we have, starting at neon, okay, we have 3s2, 3p5, okay. I mean, it has 7 valence electrons, which makes sense. And now let's see if we actually have the name chlorate, a chlorate ion. That's what I'm thinking it is. Okay. And with that being said, let's see for the orbital, oxidation number. Okay. Chlorine, as we said, oxygen, In this case, this is a rare case where chlorine would actually be a bigger bully than oxygen. That makes sense. Because these ones you kind of have to, I guess, work your way around. But in a sense, let's just say it's 2. Okay, we don't give it a charge yet. 6. Chlorine, we know it can give away 7. Okay, I mean not give away. We know that it has an oxidation number of 7. Whether it's plus or minus 7 depends. So we have 7 and 6. To get -1, the 7 needs to be negative and the 6 needs to be positive. Okay. And now I know this is kind of just a workaround, but the goal here is just to make sure it makes sense of how we can get a -1 charge. Okay. So with all that being said, this I do believe is a chlorate ion because this is what makes sense. Okay. So now that we've gotten that out of the way, they want the electron geometry. So let's actually start going through. Chlorine has 7. Okay, oxygen has 6 times 3, that's 18, plus 1 more electron, so that's 8 plus 18. We need 26 electrons. Okay, so let's start with chlorine in the middle, because the only one that's different and by itself. Okay, we have 3 oxygens. Now let's fill out the lone pairs. We have oxygen needs, because it's sharing 1 electron right now, still needs its 6 more. 2, 3, 4, 5, 6. Okay, same thing. 2, 3, 4, 5, 6. Well, actually, I'm gonna put that down here. 2, 3, 4, 5, 6. Okay, and chlorine is sharing 3 of its 7. Okay, 3. So then we have 4, 5, 6, 7. So once again, we have something that says I don't really care about the octet rule. Okay, and the reason why I say that is because these 2 will bond with each other for then chlorine to actually form 2 double bonds with oxygen. Okay, and now this last oxygen, okay, it's like, all right then, what the heck, I guess I'll just be incomplete. But that's where the last electron comes in, and there we have it. In fact, let's count to make sure we have 26. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So it does actually add up. Now let's see if our actual electron number for each one makes sense. So chlorine 7, that's what it usually likes to have. So now it's sharing, it's not sharing 4, so it has 4 plus, but actually in bonds we have 8 in total. 8 over 2. So 7 plus 4 plus 4, that's equals to plus, well, -1. Interesting. I'm just double checking here. We have 4, and then we have 1, 2. Let's just do the math and continue and see what's up here. Oh, I think I see what I did wrong. Yeah. And see, this is why I really don't like the chlorates, because actually, you know what? Let's stick with this. This is a little bit tricky, I won't deny. Because yes, chlorine is breaking the octet rule, because I do assume it's in the middle. Or maybe is it drawn like that? If I did this. No, but then the oxygen would be really positive. If I did this, no, but then the chlorine wouldn't want that either. Yep, we're gonna go with this as our gut instinct, because chlorine is going to be the, I guess the middle one. But let's just see here. So we have 7 minus, we're going to make sure that it's actually 26 electrons. 6 times 3, let's go 18, plus 7, plus 1. 26, yeah. And we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So we definitely have the right amount as well. Whoops. Of electrons. Okay. So with that being said, let's just do our math and just see where we get from there, okay? 7, 4 plus 8 over 4, we get minus 1, okay? Oxygen on the ends, like the 2 over here, it's 6 minus 4 plus 2, oops, not 2. 4 over 2, okay, it's equal to 0. Oxygen at the end, we have 6 minus 6 plus 2 over 2. We have also minus 1, which doesn't make sense because now these two add up to a charge of minus 2. So let me just see actually what they have for the structure. Okay. Did I miscount? Oh my gosh, I miscounted. Haha. So I had the right picture, but for some reason I did not count clearly what it actually had. So that's why it's important to really make sure that you recognize what a bond is. This right here, that's what I was not counting as a bond because of the different coloring, but nonetheless I should have figured it out. So actually chlorine only has two, well, one lone pair, which is 2 lone electrons, plus it's actually sharing, okay, 10 electrons here, 10 over 2. Okay, so 2 plus 5. That's how we get it. Wow. Oh, that was really frustrating. So yes, exactly. This is where our minus 1 charge is going to be on that oxygen end. And now let's actually figure out the electron pair geometry. So for chlorine, okay, because these are double bonds, these are only going to count as 1 each. So we have 1, 2, 3, 4 for chlorine. So chlorine's electron pair number is 4, okay? And of those 4, okay, 3 of them are bonds, and 1 of them is a non-bond. So for the electron geometry of 4, chlorine is going to, this chlorate ion is going to be a tetrahedral. And when you have 3 and 1, you actually get, if I remember correctly, it's going to be a, not trigonal pyramidal, it's going to be a, I'm going to look it up here. Investment theory, it's going to be trigonal pyramidal. There we go. Yep. This is what it's going to look like here. Trigonal pyramidal. So it's going to look like the ClO3 is going to look something like this. So we're going to form a pyramid like that. One of the oxygens is going to be a single bond. Okay, and it does have resonance because any of these oxygens could have been the single bond with the electron at the top like that. Hence how it forms kind of like a pseudo pyramid, because this is going to be like its base, the triangle, and everything's going to be pointing upwards. So with that being said, that is what chlorine is going to be. Apologies for that, because honestly that was quite the frustration of why I couldn't get that number to add up correctly even though I had the right structure. So with that being said, the electron geometry is tetrahedral. The molecular geometry, if they ask for it, is going to be trigonal pyramidal. So these are correct. So exactly, they say the electron geometry is going to be tetrahedral, okay? And they don't really go into the molecular geometry, but it depends on not only the number of electron groups, but also the number of lone pairs. Hence how I broke it down to the 3 and 1, because 3 bonds, 1 lone pair. So exactly, that's actually what we have here. 3 bonds. Yes, I do see the double bonds, but the double bonds count as just a type of bond. Hence why we just count it as 1. So, with all that being said, chlorine or chlorate ion is a tetrahedral 4-electron geometry. And now let's move on to question number 19. That was frustrating. But I'm glad we had to figure out what was going on there. The density of sulfuric acid is, so sulfuric acid is H2SO4. Density is 1.84 grams per milliliter. What is the volume of this? What volume of this will weigh 171 grams? So we have a conversion and we have what we start with. Okay, 171 grams. So in order to get what we want to make sure the units cancel out appropriately. So we have 171 grams, that's our initial weight, of H2SO4. Okay, and we know that for every mil of H2SO4, there's 1.84 grams. So we put the 1.84 actually in the denominator to make sure it actually cancels out. And we put 1 mil at the numerator. Okay, so we actually cancel this out because now the gram units are done. All we're left with is just units of milliliters. Okay, so with that being said, we have 171 divided by 1.84. Okay, and we get 92, and we're going to keep the same significant digits. It's 3 for the 171, so 92.9 mils of H2SO4, aka sulfuric acid. That's really all you have to do for this question, because it's just a conversion question. They're giving you what you start with and they give you a conversion. The trick here really is to make sure that you put in the right things in the numerator and denominator. Okay, so with that being said, 92.93. I'll still give this correctly. They do round to 93 mils. So with that being said, that's really all there is to that question. Move on now to question number 20. Okay, which of the following is a chemical formula for lithium nitride? Okay, so lithium nitride formula. Okay, so with this being said, all right, because it's named lithium nitride, we can actually go straight to the periodic table. We know it's an ionic compound based on the naming, just because if it was a molecular compound, you have to put your prefix on the second part. So like if you had, for example, trying to think of a good example, NO2, nitrogen dioxide, or CO2, carbon dioxide, there's a prefix before the oxide part. Okay, so with that being said, we have lithium. We look at the periodic table, that's just Li. Okay, and nitride, okay, remember the IDE, okay, is a part that replaces the actual ending. So we focus on what this part is, the beginning, the NRTR, okay, I mean NITR, and that is nitrogen. Okay, and because it ends with the I and not like an 8 or anything like that, it's just going to be the nitrogen by itself. Okay, so now for this we have to figure out its charge. Yes, you could also just look at the columns, but once again I'm going to use my lovely electron configuration. Starting with helium, nitrogen is 2s2, 2p3, because that's, you know, the third one in the p shell, so that is exactly 5, right? So nitrogen typically would rather just, you know, between subtracting 5 or adding 3 more electrons, it'd rather just add 3 more electrons. So that's 3 minus, because electrons are negative charge. So typically a nitride ion, typically, and I'll keep saying that because you never know with nature, but most common you'll see just N3 minus. Lithium, on the other hand, is literally actually the elements right after helium. So it would be helium 1 oops, not 1, 2s1. Okay, that's just one extra electron in its it's in valence shell. Okay, so that being said, lithium is like, it's not really that big of a deal for me to give up 1 electron. Okay, so it has a positive charge. So now for the lithium and the nitride to balance out, what you need to do there, okay, is to make sure that they have the same charge, because it's going to be a net charge of 0. So we need 3 lithium, so we have to cancel that out. So now we have 3 positive charges, 3 negative charges, and together we have lithium 3 N. And this right here is a molecular formula for lithium nitride. Okay, let's see what choices that gives us. We have A, let me actually write it down. We have A, LIN, that will not be it. B, LIN3, close but no dice. C, Li3N, which is exactly what we have so far, so it's definitely a good contender. Or D, LINO, and we know that that's definitely going to be a no, because we don't even see an oxygen there, because remember, nitride is just going to be the actual anion by itself, which is just nitrogen. So with that being said, the correct answer is, in this case, C. This is a chemical formula for lithium nitride. Let's see here. They do have that. They explain that lithium is +1 and nitride is N3. So this is correct. Okay. So now with that all being said, that was actually the last question for tonight. So I just want to thank you again for joining me this evening. It was lovely having you all here, and as I said earlier, definitely feel free to check out the links in the description below, just so you can get as much assistance as you want in these chemistry or any of the topics actually that you are interested in having discussion with one of our tutors. So with that, you have a great rest of your night, and thank you for joining me this evening.